Hi everyone, welcome to this presentation for AP Environmental Science. This is the first PowerPoint for the Energy Resources and Consumption unit. So this unit's going to be a little bit different than usual because of your resource presentations. You guys are going to learn more so from each other rather than these online lectures. But for this PowerPoint, we're going to talk about topic 6.1, 6.2, and I believe 6.3 on the next slide. 6.1 is renewable and non-renewable resources. This is a big point for the class, so you guys do need to know these. However, it's relatively simple. You just have to identify the differences between non-renewable and renewable resources and list which ones are which. For global energy consumption, we're going to look at some different maps and we're going to look at how energy is used around the planet, okay? And the enduring understanding for both of these is that humans use energy from a variety of sources, and we'll talk about all of those different sources, and they do result in both positive and negative consequences. Everything is kind of a give and take, and we're going to talk about the positive and negatives and see which of these energy resources the positives outweigh the negatives and which ones the negatives outweigh the positives. So I was mistaken. This is topic 6.4, not 6.3, distribution of natural energy sources. So just identify where these energy resources occur, where you can use certain energy resources and where certain energy resources are found. For example, where can you mine coal? Where can you get crude oil out of the ground? Where can you use geothermal energy? Where can you use tidal energy? All of those things. The vocab is rather brief, but you can stop this now and jot these down. So for this unit, we're going to look at a lot of different energy resources, and those energy resources can be used for a variety of things. They can be used purely for heat, which I'm going to call thermal energy. I might slip up and call it heat quite often, but I'm going to try to use thermal energy. They can be used to generate electricity, or they can be used for transportation. Okay, we're going to be, again, weighing the pros and cons of each of these energy resources. But in general, these two types of energy resources fall into two categories. Or sorry, these different types of energy resources fall into two categories. And those are renewable energy resources and non-renewable energy resources. And it's pretty much just like it sounds. Renewable energy resources are going to be replenished at a rate that is naturally greater than or equal to the rate of consumption. Okay, so they can be either reused or they are replenished by nature at a rate greater than consumption. Okay, think solar. There's no way that we can trap all of the solar energy that strikes the Earth's surface. The only way that we could ever do that is to cover the entire surface of the Earth with solar panels, and that is obviously impractical. Not to mention completely damaging to everything on the planet. There's more sunlight that strikes the surface of the planet every day than we can harness using solar panels. So the sun is going to be considered a renewable energy resource. A non-renewable energy resource exists in a fixed amount on Earth's surface, or it's replenished at an insignificant rate. So this would be something, a fixed amount might be something like uranium. There is only so much uranium in the crust of the planet, and yes, a little bit more uranium may get deposited on the crust from the mantle via volcanic activity, but that rate is insignificant for our discussion. And the other type of this is that they can be replenished at a rate that is insignificant. That's much slower than the rate of consumption. So this could be something like our fossil fuels. I don't know why I started writing that with an S, but I did. So our fossil fuels will be replenished over geologic time, okay? And 10 million years, 100 million years, there will be more natural gas, there will be more oil. But that doesn't really do us any good in the near future, right? So they're non-renewable for our human timescales. So essentially the two examples I just stated, solar panel is a renewable energy resource because the sun consistently shines, and we can use these solar panels that are shown here. These are technically called photovoltaic panels. We'll talk about those later. And we can harness that energy. The sun is going to keep shining, and it's going to continually renew the light every day. Crude oil is a non-renewable resource. We have to mine it. We have to drill it out of the ground. And there is, for all intents and purposes, a finite amount on the surface of the planet. It, again, will be renewed over geologic time, 100 million years from now, from all of the algae that live and die in the oceans. There will be more oil produced, but that doesn't do us any good for the next 20, 50, 100, 200 years, even though we should be shifting off of it less than 100, 200 years from now. Okay, so we're going to consider this a non-renewable resource because it is renewing at a rate that is way, way, way less than the rate of consumption. So I have this handy dandy list of all of the energy resources that we're going to be talking about in this class. And again, they fall into two broad categories, non-renewable and renewable. Your fossil fuels, so coal, oil, and natural gas, are going to be non-renewable resources, even though, like I keep saying, they will renew over geologic time. That doesn't do us any good for the immediate future. So they are non-renewable for all intents and purposes. There's a finite amount on the surface of the planet, okay? Because there is a finite amount on the surface of the planet for our lifetimes. Nuclear fission, this is typically using uranium, but may use some other alternative fuels, and we'll talk about some alternative fuels in class. That is also going to be a non-renewable resource because there is only so much uranium on the surface of the planet that we can mine out. Nuclear fusion doesn't exist yet. It's one of those technologies that for the past 60, 70 years, it's always been 30 years out. However, there was a recent breakthrough that we'll talk about in class. I believe it was November or December of last year that an article came out that for the first time they got more energy out of the nuclear fusion reaction than they put into the reaction. So this will become a game changer when it becomes available, if and when it becomes available. The rest of these energy resources are renewable. However, they have to be managed properly or obtained sustainably to truly be renewable, but we're going to call all of these renewable, okay? But they do have to be managed and obtained properly or sustainably. So we'll talk about each of these again in your presentations. So I'm going to skip it other than that right now. But for today, let's talk about some trends in energy use. Now again, remember that energy can be used for heat, again, thermal energy. It can be used for electricity and transportation. Those are your three main categories, okay? Heat, electricity, and transportation. As we transition through the demographic transition, we're going to be using different types of energy resources in general, okay? In stage one, before you have a pre-industrial society or you have an agrarian society, you're typically going to be using biomass. Most of this is going to be used for heat. That heat is going to be used to heat your homes, cook your food, warm your water so that you can have warm water to wash your clothes, take a bath, etc. Okay, so it's going to be used for heat primarily. Biomass is going to include wood, charcoal, crop residue, animal dung, etc. You might be using some coal. Okay, so there'd be some coal being used depending on where on the planet you are. Okay, if coal is readily accessible, then you'll be using it. If coal is not readily accessible, then you won't. As a nation or a population transitions into stage two, the urbanizing or industrializing stage, they will start to use heavy fossil fuel use. And this will primarily be coal, secondarily oil, and lastly natural gas. Okay, there will still probably be some biomass being used, but it will be shadowed by the amount of fossil fuel being used. And it will typically be used by the poor section of the populace. Okay, so you're going to have heavy fossil fuel use. Coal is cheap and is often readily available. So that's the first thing that's going to be used. And oil, again, secondarily. Okay. As you go into a mature industrial, you're going to continue using those fossil fuels. Oil and natural gas will probably surpass coal, so coal will become your tertiary resource. Again, depending on where you are on the planet, the local geology. If you have readily accessible coal, then you're going to continue to use coal. But if you have to import that coal, you probably will start to transition off of it, especially as legislation begins to be passed for clean air laws and everything else. And then you'll start to introduce some renewable energy resources. Again, that's going to depend on your local conditions as well, and we'll talk about that on another slide. And then finally, in the post-industrial, we're going to decrease the amount of fossil fuels and increase the renewables. If we had stage 5 on here, then our fossil fuels would be decreasing even further and perhaps even just 100% renewables. Okay, so that's the general trend that we see around the planet as populations go through the demographic transition with respect to our energy resources. Okay, in general, the demand for energy around the planet is increasing. Not only do we have a greater population size on the planet than any other time in the past and is just continuing to increase, but more nations are going through the demographic transition and transitioning from an agrarian society to a more urbanized society. We have the industrialization process that goes along with that. There is more of an access to energy resources, again, because of these two factors, right? You have, as you transition into the demographic transition, you gain access to global markets and transportation networks. There's an increased dependency on technology, especially with industry and agriculture, and the quality of life, right? The quality of life is a huge thing. Why would a person that doesn't have electricity not want electricity, right? So there's a quality of life standard with this as well. So most developing nations are transitioning to using heavy fossil fuel use. Again, they are transitioning from an agrarian or pre-industrial society to an industrializing society, and they're transitioning to heavy fossil fuel use. And again, like I said on the last slide, fossil fuels are cheap, they're pretty common, they're readily available, and in like stage 2 nations and industrializing nations, there's typically little regulations and laws around pollution and what can and cannot be used. Okay, they just haven't been passed yet because they haven't experienced the levels of pollution that result from fossil fuel use. So let's look at what energy resources are being used around the planet. Now, I know that this graph is a little bit dated, about 12 years old, 13 years old at this point, but it's still pretty representative of what is being used around the planet. Now, fossil fuels may be decreasing ever so slightly, and renewables may have increased ever so slightly, but this gives you the general idea. Okay, I would use these numbers, I would consider these numbers pretty accurate for right now. Fossil fuels make up about 80% of all energy use around the planet. Okay, so even if we account for a little bit less over this 12-year period, we're still looking at over 75%. Over 3/4 of all energy is fossil fuel. Nuclear represents about 2.7%. And then your renewables are 16.7%. And those renewables we can split up into this smaller pie. So we're taking this green pie, which is our renewables, or this green slice of the pie, which is our renewables, and making another pie out of that. And these are the percentages of all of those different types of renewable energy resources. And you see that they are pretty low. Okay, by far the greatest one on this list is biomass for heat. Again, this is using wood or charcoal or any other type of biomass just to heat your home, to cook your food. Okay, it's not energy, or it's not electricity production, it's not transportation. And then we have hydropower next, the only other one that is above 1%. All of the other renewable energy resources are below 1%, and I'll let you guys pause this now and just check out this list. So by far and away, the greatest use of energy resources on the planet is fossil fuels, and we'll talk about, again, the positive and negative effects of that, primarily negative. If we just look at the United States is actually pretty representative of that graph as well. However, you see that nuclear power is much higher than the global average, but you still see that fossil fuels makes up about 3/4 of all energy use around the planet in the United States. Again, this one is much more recent, so April 2021. So this is pretty representative of today. Among the renewables, we see a different spread. Okay, biomass is still being used pretty heavily. However, they are combining biomass from biofuels and biomass waste into this as well. Now, biomass waste, I'm not sure whether they're talking about this for electricity, heat, or transportation. I'm not sure what they're showing with that 4% here. For biofuels, I know that they're talking about transportation, and for wood, they are definitely talking about heat. Okay, you don't have a wood burning car. All right. A lot of people in forested areas still use wood burning stoves to heat their homes. Totally fine. It's a renewable energy resource, and if they manage those forests properly, totally fine. Biofuels, we'll talk about those in class, so that might be a little bit of a question mark in your mind right now, but we'll talk about those in class with those energy presentations. Wind is pretty high in the United States. Hydroelectric, also pretty high in the United States. And then solar and then geothermal is pretty low. Okay. And one thing I do want to notice, or want to point you towards for this graph, is that this is all adding up to 100% of this green slice, which is only 12% total. Okay, so these percentages are a little bit misleading because they are 22% of 12%. Okay, so keep that in mind. All right, for this graph, we're looking at energy use per capita. So how much energy we're using per person in a population. Now the colors on this I think are a little bit odd because they're going the opposite as what I would traditionally or usually think, but let's just run with it. Okay, if we're looking at these warm colors, right, red, orange, and yellow, we have very little energy use per person, okay, per capita. We're looking at primarily Africa, South and Southeast Asia, and Latin America, right? Energy use per person is really, really low. Also, Eastern Europe, China, Central Asia, etc. Okay, moving into the yellows. Okay, even Western Europe is primarily in this yellow color, right? It's only until you get into Northern Europe where you start to get some of the other colors, Central and Northern Europe. Okay, but let's just pause and talk about that real quick. First off, Africa, Latin America, Southeast Asia, countries that are going through the demographic transition in either stage 1, stage 2, maybe getting into stage 3. Okay, so energy use is going to be pretty low for those populations. One of the other things that you should notice is, right, if we put on some very rough Tropic of Cancer, Tropic of Capricorn lines, and equator, I know that this is probably a little bit off, but if we put on, just looking at the tropics, energy use is going to be relatively low in the tropics because you're not going to be using as much energy for heating your homes. However, you may be using a lot of electricity for cooling. Okay, so for air conditioning. That's what we see here. Okay, the wealthier parts of the Near East or the Middle East, we see a lot of energy use primarily for cooling. It's also what we see in Taiwan. Okay, industrialized nation, and they're using a lot of electricity not only for industry but for air conditioning. Okay, so in the tropics, we're not looking at heat. We are looking at heat a little bit to cook your food. You have to have heat to cook your food. But in terms of electricity, we're not heating our homes, but we're using AC. We're cooling our homes. Okay. As countries in the tropics move through the demographic transition, air conditioning is going to skyrocket. And that is going to place a huge demand on electricity, and that's going to increase the amount of electricity use in the tropics. Okay. Moving out of the tropics and out of the warmer colors, let me just erase all of this. So into the cooler colors. The cooler colors are representing your higher energy use, okay? Whether you're in that green or light blue or the dark blue and purple. The US, surprising to me, is actually in this light blue, right? We tend to think about the US as the most consumptive nation on the planet, and in many cases we are, but not quite that much as in terms of electricity per capita. Okay, but still pretty high. If we look at a couple other nations that stand out, check out Iceland, Norway. They're in this purple color. Okay, Finland in the dark blue, Canada in the dark blue. The one thing that you should see in common with all of those countries is that they are very far north. They're going to have brutal winters. Okay, that's why per capita Canada uses more electricity or more energy rather than the United States, because in general they're heating their homes throughout the winter. Same thing with Iceland, same thing with Norway. What is this, Svalbard? It belongs to Norway, I believe. Russia, not quite so much, because there are some parts of Russia that are still quite poor and quite destitute, and the nation itself has gone through the demographic transition, but some parts have been sort of left behind in that sense. So Russia, energy use per capita is actually in the middle. Okay. So in general, what we see is that industrialized nations use more electricity. So as you go through the demographic transition, you use more energy per person. As you move out of the tropics into the higher latitudes, you're using more energy for heat. As you go into the tropics, you're going to be using less energy per person right now. But as these nations go through the demographic transition, they're going to start to use lots and lots of electricity, primarily for air conditioning. All right, this next graph is showing annual CO2 emissions. This one is a little bit more dated, okay, so 2014, but it's still pretty representative. A few things to point out with this graph. First off, you see a pretty decent correlation between energy use per capita and CO2 emissions, okay? Primarily in Africa. Africa energy use is really low. Per capita, CO2 emissions are really low in general. However, the same trend doesn't necessarily exist for India and China. Why? Because they are primarily a coal-driven economy, or at least they have been and still are, but are transitioning out of that. They're transitioning to a more renewable energy resource economy. Similar thing with Brazil, but with Brazil we're also adding in deforestation. Same thing with Indonesia and the Philippines. We're adding in deforestation, which is leading to CO2 emissions, primarily from removing these large tracts of rainforest and in many cases burning them as you go. The United States, we see CO2 emissions is really high as well. We rank second behind China. We have not done as good of a job of transitioning to renewable energy resources as much of Europe has. So let's talk about Europe a little bit. One thing I want you to notice, check out Iceland and the Scandinavian countries. On the last graph, they were using some of the most energy on the planet, right? Per capita, they were using some of the most energy. But their CO2 emissions are extremely low because they have transitioned to renewable resources. Iceland is 100% of Iceland's electricity is geothermal, which releases a tiny insignificant proportion of CO2 compared to fossil fuels. Okay. Similar story with the other Scandinavian countries, except for instead of geothermal, they're using other renewables. Canada also doing a pretty good job of transitioning to renewables. You notice that Canada CO2 emissions is less than the United States. Now Canada also has a smaller population than the United States. This is not CO2 emissions per capita, this is total CO2 emissions. So a smaller population in a country also plays into this, where it didn't in the last slide. But just a couple things to think about. So one more pie chart related to CO2 emissions. This is actually just greenhouse gas emissions total, so not necessarily just CO2, but other greenhouse gases as well. This is from the Climate Data Explorer and Environment Canada. So this is like a Canadian government resource. So they do point out Canada and talk about Canada by sector. But again, what you see is that China is the #1 polluter of greenhouse gases or emitter of greenhouse gases. The US is #2. India is #3 if you go by country. And then Europe totals 9.8%, so it's greater than India, but India is one country, whereas Europe is many different countries, even though the EU is a thing. Anyway, Canada, only 1.6%, but we see what their distribution or their breakdown is. So transportation is pretty high, oil and gas pretty high, buildings, believe it or not, and then electricity generation, industry, agriculture, oil sands, they highlight for some reason. We'll talk about what oil sands or tar sands are, and then some other resources. But just to give you a different distribution than last graph, but essentially the same content. So one more map. This one is a little bit difficult to read. It's a little bit blurry and a lot of these circles overlap one another. But what we're looking at is our power plant distribution around the planet. This is a little bit dated as well, so this is looking at 2012, so some things have changed in the intervening 10 years, but still relatively representative. And we see our different energy resources plotted out on the map. The size of the circle represents the installation capacity, so the size of that power plant. And what we see is the distribution of, again, our fuel types, our energy resources. So a few things to highlight here. One thing that I want to start with is coal, wherever that is. It is this brown color. So look at the distribution of coal. It's hard to see because that brown gets hidden by some of the other colors, but we're starting to see less and less and less coal being used around the planet. Look at the United States. Very little coal being used. We see some coal, I'm getting up into Canada there, but United States and Canada, we're seeing some coal power plants, right? But it's less and less, and it's drowning out in a sea of these other colors. South Africa, you may have noticed the CO2 emissions were pretty high on the last page, uses a lot of coal. There are coal deposits, I'm sure, in South Africa, which is why they're using them. If they didn't have those deposits, then they'd have to import them, which they may be doing. But in terms of local geology, where you have coal to mine, you are going to have coal power plants. Or where coal is cheap to transport in, maybe coal being mined from Eastern Europe and transporting into Central Asia via rail networks, you may have more coal being used. Now that may change due to social political events and war in Ukraine that's happening right now, and sanctions with Russia and all that stuff. But in general, I'm going to skip over the social political stuff and just focus on the graph. You see a lot of coal being used all throughout East Asia, China specifically, and India as well as Australia. You see some of these brown installations. Okay, let's look at another one, hydro. Notice Brazil. Brazil uses a ton of hydroelectric power. They have a lot of water, so they have a lot of running rivers. They're going to be using a lot of hydroelectric power. The western half, or the western part of South America as well, in the Andes and west of the Andes, a lot of running rivers and a lot of changes in elevation to power those power plants. You see that throughout Central America as well, and then up into the United States and Canada, you get a lot of hydroelectricity as well. Okay, think about the Colorado River, the Columbia River, etc., in the western United States. You see a lot of hydroelectric in Africa too. Check out everything running along the Nile. You see hydroelectric power plants. Okay, Central and Eastern Africa, right? A lot of hydro. Check out Norway. This is why Norway is so This is why Norway is emitting so little carbon dioxide, is because of all of that hydro. They're showing a lot of hydroelectric in Iceland as well. I was under the impression that Iceland is 100% geothermal. Maybe they have transitioned to that, but maybe I misunderstood what I was reading. And Iceland also has hydroelectric and geothermal and is 100% renewable rather than 100% geothermal. But in either case, Iceland is 100% renewable, whether that's just geothermal, which I doubt it is now looking at this graph, or if it's hydroelectric as well. All right, sorry about that. And then finally, notice what's going on in Asia with hydroelectric. Around the Himalayas, Tibetan Plateau, lots of hydroelectric installations, lots of hydroelectric dams. And then in East Asia, China, Southeast Asia, a lot of hydroelectric. Okay, some of the largest hydroelectric dams, you should know Three Gorges Dam in China, and you should know the Aswan High Dam in Egypt. And we'll talk about both of those in class and some of the environmental effects of both of those. Okay, so hopefully you have that down. I'm going to erase it. And then just take some time, pause this. This PowerPoint is going a little bit further, a little longer than I thought, but check out the other renewable installations, right? Solar and wind. Notice that much of Europe is going towards solar and wind. Much of the United States is transitioning to solar and wind as well, but the United States still is very heavily reliant on natural gas, especially the central United States. Colorado is not exempt from that as well. We are primarily a natural gas state. All right. See if you can find any nuclear installations around the planet, right? There's a couple in the US still. I mean, we still get quite a bit of a fair amount of our electricity from nuclear. You notice a very large one here in Brazil. Some of the largest nuclear power plants are in Eastern Europe and Russia. You may have heard about those on the news. And then France. France has a very high proportion of the electricity from nuclear. And then Finland as well, and Sweden. So lots of nuclear being used also. But again, pause this, check out these resources. And some of them may surprise you, right? Why don't you see tons and tons and tons of solar panels in the Sahara or the Arabian deserts, right? Why do you only see little small pockets of solar panels in the outback? Okay, some of these types of questions should be coming to mind. We'll talk about those in class. Again, we'll especially with solar panel distribution, we'll talk about some of the challenges for infrastructure cost. All right, so couple more things. The units for this unit, we're going to be using a couple different units that you'll see throughout this unit. The first one is watts. This is a unit of power. It's named after a person. In fact, joules is also named after a person. I forget both of their first names off the top of my head. But it's a unit of power. Specifically, what we're going to be using it for here is a measure of rate of energy transfer. Okay, specifically for electricity. You may have seen on your light bulbs that they are measured in watts. You may have seen on your electronic devices that they're measured in watts. Okay, we can measure watts in kilowatts, megawatts, or terawatts. You should know those. Okay, remember that you should know for this class pico to, in this case, tera. Okay. And then finally, for watts at least, is kilowatt hour. This is 1 kilowatt of power sustained over 1 hour. So you'll see that in domestic energy use or commercial energy use or for the energy production of a power plant. If a power plant is producing 100 terawatt hours, you should know what that means. So it means that they're producing 100 terawatts consistently over 1 hour. Okay. And then you'll probably see some questions where you have to convert that into how much electricity are they converting, or how much electricity are they making in a day, how much of the electricity are they making in a year, et cetera, just with dimensional analysis. But we'll do some practice for that in class. Joules, this is a unit of work. Specifically, what we're going to be using it here for is work performed by machines or electronics. Okay. And then finally, a British thermal unit. This is a unit used for heat. Okay, and the last point that I want to make here is a little bit of a sidetrack. This is the total cost of goods. We've talked about externalities before when we discussed the tragedy of the commons, I believe. The total cost of a good is also known as the full cost, and it's the cost of a good that includes all of the environmental effects of that product and the externalities of that product. Okay, so an externality is the cost or benefit that the producer incurs but is not paid for by the producer. It's paid for by everybody else. Okay, the pollution at the power plant or the pollution at the factory is paid for by everybody else that's breathing in that air, not necessarily the producer, depending on local regulations. Sometimes they have fines for too much pollution, sometimes they have tax breaks for less pollution, but in general, that pollution could be an externality. Okay, consumers, we almost never pay the total cost. Why would a company voluntarily make us pay the total cost and have their product be higher? But as we'll talk about in this class, we probably should be as a way to de-incentivize companies to pollute. Okay, so let's talk about a refrigerator. Okay, when you buy a refrigerator, you pay for the cost to produce that refrigerator. You pay for all of the parts and materials and everything that goes into that refrigerator. You pay for all the manufacturing of it. You pay for the employee salaries. You pay for the packaging, the cardboard, the styrofoam, etc., and the packaging. You pay for the transportation, getting it from the factory to the store. And sometimes that transportation is covering vast distances. It might be a refrigerator that was made overseas, so you have to load it from the factory to the docks via a truck or a train. Then you have to load it onto a ship, transport it overseas to a harbor, and then let's just say that you're living in Colorado. Then you have to take it from a landlocked state for all of my non-Colorado viewers. So it arrives at a harbor, you have to put it on another truck, get it to the store in Colorado. The transportation costs can be huge. Plus, you're paying for the company's profit, right? You're paying for the bonuses that the CEOs and the board executives are getting, right? In most cases, you're not going to be paying for the externalities, though. Those externalities will be the disposal of the packaging. You are not paying, when you pay for a fridge, you're not paying for the disposal cost of the styrofoam and the plastic and the film plastic and the cardboard box that you get when you buy that refrigerator. You're not paying for the disposal of the fridge at the end of its life. Typically, you'll have to go back to Home Depot or Lowe's or wherever you get your refrigerator and pay them another $100 to dispose of it. Okay. You typically don't pay for the coolant pollution that may occur if it's breached. You don't pay for the factory emissions, again, given local regulations, transportation emissions, etc. So again, we'll unpack this a little bit more in class. I'll have an article for you guys to read, also given or talking about the total cost of goods and some other ways that we can model this in our economies. Okay, but for today, just wanted to give you that brief introduction on it. So again, a little bit of a side note, let's get back to the learning objectives. So you should be able to tell me what the difference is between a renewable and a non-renewable resource is. So a non-renewable energy resource is anyone that exists in a fixed amount on the planet and involves energy transfer that cannot be easily replaced. Okay. There's only so much on the planet and you're not getting more and more. It's not being replaced. Renewable energy resources are those that replenish naturally. So we could be talking about sunlight, wind, the tides, trees growing, or near the rate of consumption, or they could be reused. Okay. For this second one, global energy consumption, this was mostly looking at the maps and charts that we had. The use of energy resources is not evenly distributed between developed and developing countries. Again, demographic transition model. The most widely used energy resource is still fossil fuels. Renewable is still a very small proportion. As developing countries become more developed, their reliance on fossil fuel for energy increases. So they move from biomass to fossil fuels. And then as populations grow, you need more and more fossil fuels. And then as the world becomes industrialized, the demand for energy increases. And the availability, price, and government regulations influence which energy sources people use and how they use them. Okay, so we're talking about availability. So is coal or oil readily available, or do you have a giant river that is just rushing nearby that you can build a dam near, or a dam across? The price, is energy cheap? Is it affordable? If you have cheap energy, you're going to be using more of it. And government regulations. Okay, so governments, especially in developed nations, are transitioning from fossil fuels to renewables. They're giving incentives like tax breaks or subsidies for people to install renewables at their homes. They're putting up a lot of money to convert old or dismantle old fossil fuel power plants and building renewable power plants. Okay, so that's something that's happening at the government level. So the last learning objective is identifying where natural energy resources occur and the global distribution of natural energy resources such as ores. For that, we're usually talking about uranium, but other fuels as well. Coal, crude oil, and gas, it's not uniform. It depends on a region's geologic history, okay? As well as other physical features. If you don't have a river, you're not going to be doing hydroelectric. If you're a landlocked state, you're not going to be using tidal energy from the ocean. If you are, if you have a huge deposit of coal nearby, you're probably going to use that coal because it's relatively cheap to mine and you have little transportation costs. Okay, so what's going on with wherever you are geologically is going to influence what energy resources you use.